So good day. So today I will discussing Laboratory Experiment 1, CPE109L Embedded Systems Laboratory, Section E01, under Engineer Cyrel O. Manlises. So I am Laurence B. Navarro, CPE109L, Section E01. So today I will discuss first the step-by-step procedure of the laboratory experiment 1. Second is debugging of the program. Third is questions provided in the PDS such as A. Introduction, B. Objectives, C. Materials, components, and software used, and D. Procedures. And lastly, answers to questions. Step-by-step procedure. So for the video demo, I will demonstrate the laboratory experiment 1 on how to accomplish the questions as well as the procedure. So for the part 1, so first is to launch the NI Max from the Windows Start menu. So NI Max. Create simulated hardware. So in the NI Max, select devices and interfaces, and click the create new button. So right click and then create new. So select simulated and IDEQ MX device or modular instrument and click finish. So select simulated and then click finish. So once this pop up, so expand the M series DAQ and then select NI PCI 6221, which will be used in the experiment. So 6221. Then press OK. Once it is selected, go under Settings section and click Device Pinouts and explore the pinout information. So go to Device Pinouts. So Device Pinouts. And then explore the pin configuration. So this is the pin configuration for the part 1, which will be used in determining the analog inputs, analog outputs, as well as the digital I/O ports. So for the part 2, so close the pin information. So for the part 2, um, first step is to click the test panels. So test panels is located in the same pane of the device panel. So device pin out. So click test panels to validate the analog input of the device. So once this pop out, select channel name, select dev1 /AIO. So for the mode, select continuous in order to modify the values of the measurements. So once it is, so by default, we can start um, the acquisition. So by starting the acquisition, the waveform will run. So there you go. So one of the instruction in the laboratory manual is to change the samples to read to either 5,000 or 10,000 to see the differences. So let's stop the running of the program. So change the samples to read to 5,000 and then click start. So as notice, the values start from 0 to 10, and then from 10 back to 0, then from 0 going to -10, then -10 going to 0 again. So this forms, when connecting all those waveforms, it forms a sine wave. So So therefore, the samples to read really affects the signal of the output signal. So here ends the demonstration of the laboratory experiment 1 procedures. Second is debugging the program. Since the program is not applicable, and in the experiment, um, analysis of the signal waveforms was conducted, there was no debugging occurred in the experiment 1. So here is the questions in PDS. So first is the introduction. So NI measurement and automation, Explorer, um, or also called NI-MAX, allows to examine, configure, and simulate NI hardware, which is usually installed along with application development environment such as LabVIEW. So NI-MAX allows us to understand the different NI devices such as NI6221 and etc., their pin and configurations. So the laboratory experiment 1 tackles on understanding the NI hardware, specifically NI6221, its waveform behavior, and their input and output configurations. So it also gives an introduction and familiarization regarding the softwares of national instruments such as NI-MAX and LabVIEW 2020. So for the objectives, Um, first is to use NI Measurement and Automation Explorer to examine, configure, and simulate NI hardware. So the students also familiarize the Software LabVIEW 2020 and NI-MAX for the next laboratory experiments. So the students also verify that the I/O or the input output of our DAQ device behaves correctly in terms of their signal waveforms. And lastly, the students were also able to learn how to interpret graphs and understand different functions of the measurements and its effect in the resultant output waveform. So for letter C, materials, components, and software use, software used in this laboratory activity was NI Measurement and Automation Explorer, or NI-MAX, used to examine on a DAQ device, particularly the NI-PCI 6221. So the software application LabVIEW 2020 was also introduced, and some of the concepts on how to use the front panel and block diagram was discussed in the video lectures. So for letter D, procedures. So part 1. So for the part 1, the first step is to launch an IMAX from the Windows Start menu. So as seen in the figure. Second is to create a simulated hardware. Select an IDAQ MX device or modular instrument. So third is to expand M-Series DAQ3 and select an IPCI 6221. Fourth is to expand devices and interface and select PCI 6221. Under the settings, click device pinouts. So there you go, the device pinout information will pop up in your screen, and you can see the pin configurations of the PCI 6221. So for the part 2, first is to click the test panels on the settings window pane. So second is to validate the analog input of the device. Select PCI 6221 /AI 0 from the channel name and change mode to continuous to enable the measurement settings. So third is to click the start button to start the acquisition. So the next part is the answers to questions. So for the first part, the first question is to list all the pins that can be used as input and output port. Tabulate the pin on the type signal, digital or analog. So for the part 2, there are two questions. First is to capture at least 3 waveform signal. What did you observe to the waveform in the graph? And then change samples to read to other values. Example, 5,000 or 10,000, etc. And then start the acquisition. So the second question is to capture the acquired signals of the other values. how the samples to read values affects the acquired signal. So for the part 1, list all the pins that can be used as input and output port. Tabulate the pin on the type signal, digital or analog. So here, I was able to arrive and answer the question by checking the labels of in the pin configuration. For example, the label starts AI. It means that the pin is an analog input. However, if it is AO, it signifies that it is an analog output. However, if it is PFI or letter D, starts with letter D, or the ports, it is considered as digital signal input output or digital input output. So in summary, AIO up to AI15, it is considered as input analog, shown in the table. So AO0 and A01 is considered as output analog. So for the pins, port 0.0 up to port 0.7, PFI 0/P1.0 or port 1.1 up to PFI 15 or /P2.7, they are considered as digital input/output or digital I/O. So basically, um, um, analog input are 16 in total, while the analog output are 2 in total. And lastly, the digital I/O are 24 all in all. So for the part 2, capture at least 3 waveform signal. What did you observe to the waveform in the graph? So as seen in the PowerPoint, figure 1.0 or the first waveform signal. So the signal shows the amplitude which is set to a max limit of positive 10 and a minimum limit of negative 10. Versus the sample chart which was set to 1000. So the step value of each of the output displays on the graph is by 1000 because of the set values or the samples to read. In the first waveform of the signal, which is from the first 1000 samples, the amplitude reaches in between 6 and 7, as shown in the figure. For figure 1.1, or the second waveform signal, the second waveform signal, which is from 1000 sample up to 2000 sample, the wave starts from 6 up to 9.5. However, from the third waveform signal, it shows the 2000 sample up to 3000 samples. The output was also able to reach the peak or the maximum amplitude, which is 10. So the signal also starts to decline in the third output. The next video shows the continuous running of the waveform. So capture at least 3 waveform signal. What did you observe to the waveform in the graph? So the output waveform is an example of an analog signal. As observed from the continuous running of the signal, after the signal reaches its peak, it starts to decline. After a samples of decline, once it reaches its trough, it starts to rise again, which forms a sine wave. So the waveform also contains heavy noises, which makes it hard to determine their exact and definite values. So part of the experiment also asked the students to change samples to read to other values, for example, 5,000, or 10,000, or etc., and then start the acquisition. So changing the samples from 1,000 to 5,000 results to numbers of each of the output displayed increases, which makes the waveform clearer than the previous waveform. So the first waveform, which is from 0 samples to 5,000 samples, the waveform already reaches the peak or amplitude, which is 10. So running the program continuously will show the output faster and clearer since the number of samples in each of the output was increased. Question 2 is to capture the acquired signals of the other values. How the samples to read values affects the acquired signal. So for figure 2.1 shows the first acquired signal, and figure 2.2 shows the second acquired signal. So the samples to read values determine how many samples will be read in every output displayed. It affects the quality of signal of the waveform since larger values of samples renders a large amount of waves. Hence, it provides a clearer image since it provides many samples in every output. The output waveform signal is faster in terms of display. So for example, when the samples to read is set to 1000, the wave will reach the peak in its third output. However, when the value is set to 10,000, the waveform already reached its peak at its first output. So shown in figure 3.0, when samples to read is set to 1000. So as noticed in the x-axis of the graph, um, the maximum value is 3K, wherein samples to read is set to 1000. So 3000 dividing 1000 will be equals to the total number of outputs in the graph. So therefore, it reached at least 3 outputs to reach its maximum peak or the positive 10. So, however, when samples to read is set to 10,000, at the first output, the signal already reached the maximum peak, which is 10. So, here ends my discussion. Thank you.